Hello, everybody, to Thermal Engineering Concept and the Principal Kernel. This is Professor Ali Tarrad. I will introduce to you the thermodynamic treatment for Rankine cycle. So, in this episode, I will give summarized introduction to the thermal treatment and energy conservation of the system. And how can we apply the first law of thermodynamics to the components of Rankine cycle? The objectives of the present episode is related to the Rankine cycle structure and what are the main components. We will talk about the first law of thermodynamics, which is applied to solve the problems related to the components of Rankine cycle structure. And then we will apply the first law of thermodynamics to each of the components of the Rankine cycle. Finally, we will approach the closure of the present episode. Now let us discuss Rankine cycle. Rankine cycle, the thermal cycle, composes of 4 different thermal processes, and there are 4 components. We have boiler, turbine or expander, condenser, and pumping system. The objective of this cycle is to convert energy from external source to electricity. Usually, energy is extracted from burning out the fuel, such as fossil fuel, coal, oil, or natural gas. And then the energy of this process is extracted by water, for example, when we are talking about steam power plants, and this water is converted to steam. Usually, the vapor which leaves the boiler is in a superheated condition. This vapor passes through the turbine, and the turbine usually is composed of multi-stages, and it extracts the energy that is stored by the steam and convert it to a dynamic energy where the blades inside the turbine extracting this energy and convert the thermal energy to mechanical energy. And with the aid of a generator, we may convert this rotation energy to electricity. Usually, the fluid which leaves the turbine is in a mixture condition that is composed of about 92 to 94% dryness fraction, and that means there is some liquid is leaving the turbine, and this mixture, vapor liquid mixture, is passing through a condenser where it is condensed, and we can achieve this process by passing a cooling water through the condenser, which can be withdrawn from a river, lake, or even a cooling tower. Condensate is pumped by a pumping system which uses a motor with a power supply. Then the liquid is pumped to the boiler. So in that sense, we will get a closed circuit for the working fluid inside this cycle. Now let us talk about the thermodynamics of the Rankine cycle. For example, we have here the main components of the cycle, and this diagram is for simple organic Rankine cycle, and it could be the same for even steam power plant, the same components. So we have the TS diagram. So we have two processes where we have energy in the boiler, and we have energy out in the condenser, plus the work done in the expander or a turbine. And we have a power consumption to operate the pump. So in that cycle, we have two processes are considered as isothermal in the evaporator and the condenser, and two processes where we have isentropic process for the ideal cycle. The thermal efficiency usually for these cycles is calculated from the power output work dot net, which is the difference between the output in the expander and the consumed one in the pump, divided by the energy extracted in the boiler. So in general, we have for a coal and oil fired cycles an efficiency about 37%, and for the combined cycles where we have the gas turbine plus the steam turbine to get a thermal efficiency up to 60%. We have here the description of the first law of thermodynamics. We have here a system where we have a gas and it can be compressed in relation with the surrounding. Then we have heat transfer, and work can be done to get the final state as shown in state number 2. The general expression for such process is delta U equal Q minus W. And that means the first law of thermodynamics can have the expression shown in equation number 1. That is Q dot minus W dot equal to the summation of energy out minus summation of energy. So in this way, we may predict the energy through a system, whether it was boiler, condenser, or expander, or even a pump in this general equation as shown in equation number 2. And this represents the conservation of energy for the system. Now we will apply the first law of thermodynamics to the evaporator or the boiler as shown in this figure. In the boiler, we convert liquid to vapor. Liquid enters at condition number 2 and leaves as a vapor in condition number 3. And with that process, we extract energy from another source. So the general equation as represented by equation number 2. To solve this uh, expression, or to simplify this expression, we have some assumptions. The hydrodynamics effect as a result of the velocity change is negligible. Then we have the effect of level between the input and output sides of the heat exchanger is neglected. And for this equipment, the evaporator, there is no moving parts, so there is no work done, then it will go to zero as well. And the process in the evaporator is assumed to be isothermal in the evaporation part of the heat exchanger. And that means we have a constant temperature. And then finally, there is no heat losses to the ambient, then it will be set to zero. These assumptions are applied to equation number 2, and then we will get the final expression for the heat transfer rate in the evaporator equal m dot times H3 minus H2. We may apply the same concept of the evaporator here in the condenser. In the condenser, we have vapor enters the heat exchanger, which is converted to liquid. And to do that, then we have a cooling medium, such as a cooling water from a cooling tower. And again, we have the same expression of the first law of thermodynamics, which is represented by equation number 2. And we have the assumptions here, which are similar to those used in the evaporator. We have the hydrodynamics effects are negligible, so the velocity effect is negligible. Then we have the elevation effect is ignored, and there is no moving parts of this equipment, then there is no work. And we have the condensation process in the condensation section of the heat exchanger is isothermal, and then we have no heat losses to the outside because this heat exchanger is well insulated. And finally, we will get the equation which represent the thermodynamics of the condenser to be Q dot condenser equal M dot times H4 minus H1. And don't forget that the values of H represent the enthalpies of the working fluid. The turbine or the expander, as shown in this figure, we have the inlet and outlet, and the vapor enters the turbine and leaves as mixture or even superheated. It depends on the working fluids for example, for the organic cycles, we have three different types of fluids, whether they are wet or saturated or superheated. But for steam, usually the steam leaves as mixture, which is some liquid um, goes out of the turbine with the steam at low pressure. And then the energy stored in the steam is converted by generator to produce electricity. And if we apply the same as equation number 2, then we will get um, similar equations, but here we have the work is a factor. So if we ignore the elevation effect and the velocity kinetic effect, uh, then with the assumption that there is no heat loss to the ambient because usually these turbines are well insulated, then we may get an equation which represents the work done by the expander equal to eta sub V expander, which represents the volumetric efficiency times m dot times the difference between the enthalpies at the inlet and the outlet of the turbine. And we may express the isentropic efficiency by equation 5b as shown in this slide, and values for uh, the thermal isentropic efficiency of the expanders may approach 90%, and for small turbines may have an isentropic value uh, below 70%. And now we reached the last part of this cycle of Rankine cycle. It is the pumping system. So if we have the pump, we have a condition in and condition out, condition in with enthalpy H1 and condition out with enthalpy H2. And to operate this pump, we need a motor which extracts uh, electricity from an external source. So the final case of this uh, equipment or this component of the cycle, W dot pump equal M dot H1 minus H2. And these are the enthalpies of the uh, fluid, circulated fluid. And we have also the isentropic efficiency is defined by equation 6b, which represents the isentropic difference of enthalpy divided by the actual enthalpies. And we have the efficiencies for isentropic efficiencies for these uh, pumps can range between 75 to 85%. Dear friends and followers of this channel, now we arrive at the final part, which is related to the closure of this episode. In this episode, we explained Rankine cycle and what are the principal components of this cycle. First law of thermodynamics and how can we apply it for the four components of Rankine cycle. And we explain how can we derive the main objectives of the thermal analysis, which is related to the thermal efficiency of these cycles. In fact, there are some references and tools are available in the description box down in this episode. If you found that the content of this video are useful to you and others, please subscribe and share the content with others, because our objectives is how can we reach everyone who needs these information. And thank you for listening, and I will see you in the near future for more episodes in the thermal engineering. Bye-bye.